creating some shortcuts. Thank you. We could do so by creating some shortcuts like categories or selective attention, to reduce this information overload. That is okay for efficiency purpose, but then that is going to obscure the facts to some extent. So that means this kind of cognitive efficiency is going to sacrifice accuracy. And there's a third explanation. It's about representation. The people tend to think that, we have social groups, either they are bigger in size or smaller in size, majority group or minority group. It's a natural consequence of statistical learning. When we don't have a big enough sample size, we are going to make some inaccurate inferences based on small sample size. So people may say, the reason we have inaccurate stereotype is just because some groups are smaller in size. That is plausible. All right. Now, in contrast, actually, my work contrasts with all of the three prior explanations. Now, we want to provide a new kind of explanation, which is about adaptive exploration. I'll talk more about that, what that means later. But what's unique about this idea is that it's much simpler. Here, we don't require any of these previous assumptions, but we are still going to see biased impression, inaccurate stereotypes emerge. Now, because the kind of process I'm talking about will be a sort of fundamental, a general process in the sense that, just to give you a high level overview here, which is, it's about people are going to make new decisions based on their past experiences. That's it. It's actually that simple. This simple process is going to create bias in the end of the day. So I'm going to show this kind of seemingly innocent and almost rational adaptive exploration can lead to detrimental products like societal level biases. Now, let's just dive into what I mean by that. Now, first, let me give you a formal, an intuition behind the key psychological idea. What do I mean by, adaptive exploration lead to inaccurate stereotype? And then I'm going to rigorously define this intuition with computational modeling and simulation. And then we'll come back to look at some human experiments, because actually psychologists care about human empirical data. And then we can come back and discuss about implications. So let me just say, I'm happy to take all the questions throughout the talk, clarification question, whatever is on your mind. And I probably cannot see my chat. Let me see. If I can monitor it, but if there's no chance for me, if someone can help me to monitor the question, just feel free to jump in anytime. All right, now let's look at this intuition game, this key psychological idea. Now imagine this is an everyday interaction. There are 4 groups of people. They are indicated by different colors. And the numbers here represent their average warmth, like friendliness. For example, if there are 100 people in each group, then 90 of them will be friendly and 10 will be unfriendly. So that means there is no group level differences. Now, I'm going to assume that we give each group a distribution to represent their warmth, like the thing on top. And this distribution will change as we collect more evidence. Now say, if you want to work with someone in the future, but you don't have any information about these groups right now. Now, what you can do, imagine you are this little person here. Now, what you can do is perhaps to ask a small favor from one person one at a time. Now, if that person helped you, you can give a thumbs up. If not, you give a thumbs down. And all these past experiences is going to change your impression about these groups. Now, let's make it a little bit more concrete here. I'll say I don't really have any preference for now because I know nothing about these groups or whatsoever. I just want to randomly start with red. I will ask a favor from a person from the red group. Can you help me? How can you help me or something like that? And it turns out, yes, I got a thumbs up. Awesome. I'm going to update my impression here. It's getting, closer to this, more warm kind of end of this diagonal. All right, now maybe I want to ask a second time because I got successful experience last time. How about we do that again? Thumbs up. Awesome. Update my impression. But because I'm not particularly biased toward red, so I may just want to switch to some other groups. How about let's try blue? Let's do that. Thumbs down. That's too bad. Maybe you want to change to yellow. Let's try that. Thumbs up. Awesome. Try again. thumbs down, update per impression. Now, it seems like red is helping me more, so I may just want to switch back to red. How about let's do that? Thumbs up, awesome. Try again, thumbs up. Now, in the end, we will probably form this kind of impression that red helped me the most. Then I think maybe red is probably warmer than other groups. Now, however, if you still remember that we set warmth to be identical across all groups, 90%, that was the ground truth. But we didn't have biased motivation. We didn't want to demean any group during the process. We kind of followed the exact information updating process. We got information, we update the distribution, we just do that. Even though everything seems perfect, it's fine. But in the end of the day, we still got this somewhat differentiated perceptions about these groups. And that is what we propose here, as adaptive exploration locally leads to inaccurate impressions globally. Now, just let me clarify what is unique about this idea here. Those are the past explanations. Now, first, we don't need this motivational bias, right? Like, we didn't really want to demean or oppress other groups. Like, the only thing we wanted to do is to maximize the chance of being helped. And second, we don't need this cognitive limitation here. Like, for example, like in the classic explanation for why do people have stereotypes about minority group, for example, in the US, people tend to say, some negative attributes associated with African-American. People tend to say one explanation is that, we selectively attend to negative information because it's kind of alarming, and we ignore those positive information, and that is why we have the stereotypes. But if you remember, throughout this process, we don't have that. We just take all the information we have, either positive or negative, whatever. We just take all information we have. We do this Bayesian updating process. I'll explain later. But this is a rational updating process. But still, we got this, differential perception in the end of the day. And third, we don't need this unequal sample size assumption either. In our game, we have 4 groups. Each of them is equal in size, 100 participants in each group. So we have a perfect and balanced and diverse sample. It doesn't matter. We still got this differentiated perception, the biased perception, that red is the most important, the most trustworthy group, right? So as the audience, we kind of have this this bird view, this God's perspective, like we know, all groups should be the same. But then if we're really the kind of decision maker who are doing this game, in the end of the day, we may form this bias from this kind of adaptive exploration. And that was the key idea. Now, in the next couple of slides, I'm going to be a little bit more precise here. So I would try to say, if you are more like intuition-oriented audience, then don't worry about the next 5 slides because everything I'm going to say is going to be repetitive. But then if you're a more quantitative audience, which I assume most of you are, maybe you want to pay attention to, what is really happening under the hood, what is the math, what is the precise prediction. Now, what we did, this interaction thought experiment, is actually a famous problem in the reinforcement learning. It is called explore, exploit dilemma. In that game, we have a dilemma, which is that we were constantly facing the problem of deciding whether to explore new options because they might be better, or to exploit our past experiences. Now, each group is configured with an unknown probability of how likely you'll get a reward at one play. So the question to you is that what is the best strategy to achieve highest long-term rewards? There are many ways to solve this problem, but we actually did one solution. If you think back, like what we did, if red helped me more, then I am more likely to select a new red, but not always. Sometimes we're going to explore some new groups. That actually is one solution to this multi-armed bandit problem. It is called Thompson sampling. I'm just going to summarize at a higher level, but happy to talk more later. It's a Bayesian approach. And the idea is that for each new decision, we are going to pick a group with the probability equal to the probability of it being the optimal choice. In other words, we're going to explore to some extent, and the exploration rate will be proportional to our past experience. Now, I just want to insert, some related domain. Although, we formalize the problem of the human bias in this reinforcement learning and Thompson sampling framework, but actually this framework is also widely used in online platform. If you think about your recommendation systems, actually, most of them have this similar architecture under the hood. And then that will create a kind of phenomenon like filter bubble and echo chamber. So that we could save that for open discussion later. All right. Now, our prediction. Now here in our idea, we want to say there's no group level differences. That's the ground truth. So we have this environment structure where all groups are equally and highly rewarding, 90% reward rate. And the decision maker didn't have any prior bias. Like everybody start with a flat line, like everybody's like kind of similar. Now we can compare two different conditions so that, we know what is really happening about this Thompson sampling can inform our predictions. Now, the only difference between the two, the Thompson sampling and random sampling, is that Thompson sampling, as we said, they're always going to use their past experience to make new decisions. But now we need to see a contrast. So we have a control condition, which is random sampling. Just as what random means, that means that we're going to ignore past experience. Every time we just make a random selection. And we can compare how these two conditions are different, or maybe not different. Now, given the setup, we could do some simulations. We could look at two kind of outcome variables. First, how many times did the model, this Thompson sampling model, interact with each of the group, right? So ideally, the model should, if they know the ground truth, then they should interact with each group for equal times. But let's see how the model does. Now, second, we want to know what is the estimated reward for each group. Again, the ground truth is 90% for all of them. So ideally, the model should say, 90% in the end of the day. So we want to see how the model does. All right. Now, this is our simulation results. We're going to really quantify the intuition here. Now, let me first show you this random sampling, this control condition, just to have a baseline. If you look at this figure on this bottom left, this is number of interaction from random sampling. On the x-axis, we're seeing different groups. We have full groups. On the y-axis, we're seeing number of interactions. Actually, in the model, I trained the 40 times. And if it's random, then we should see, the interaction time should be like 10 times. And indeed, that is what we see. We found that this model interacted with each of the group for about like 10 times each, random, which is fine. Now, if you look at this figure on the bottom right, that is estimated reward. Now, on the x-axis, you're seeing times of rounds of interaction from the first round of the game to the last round, the 40th round. On the y-axis, where we have this estimated reward. Now, this is what we see. This dotted red line, this is the ground truth, 90.9% reward rate. Now we're seeing, like the estimation is approaching this ground truth, although it's not perfect, but it's, approaching the ground truth, which is good. Now, what's really critical is this Thompson sampling condition. Now there, we're seeing a pretty different picture. First, in Thompson sampling, when this agent used their past experience to make new decisions, we found that they actually predominantly and selectively interacted with one group, but underexplored the other three groups. Now, as a result, we found their estimation is also very bad. For example, it's giving a good estimation for the group it interacted the most, the red one, but it's a much worse estimation for the other three groups. In other words, we found that this Thompson sampling now think the four groups are much more different from each other as compared to this random sampling condition. All right, just to sum up about this model prediction here. So we actually found quantitatively selective interactions and bias impressions emerge when this environment gives high and identical reward, and when this agent didn't have any prior bias at all, and especially when this agent used Thompson sampling strategy, not the random sampling. All right, so that's about model prediction. But as psychologists, we care a lot, like social science in general, we care about human behavior. Even if we have a formal model, we have a formal like theoretical prediction, but if it doesn't speak to human data, then, it speaks to the validity of the theory to some extent. So we want to know about human behavior. And let me show you that. We run a large scale online experiment, and let me just explain that experiment to you here. This is our experiment. It's kind of similar to our intuition game. but we have a little bit more socially informed context. Now imagine if you are our experimental game participants, and now you are invited to a fictional city called Toma City. There are residents in Toma City. They come from 4 ancestral villages. The village called Toma, Aima, Rekun, Weki. If the names don't make sense, that's great, because we want them to make no sense. Those are the kind of novel groups. All right, now you can collaborate with Toma to earn more points. And the more points you earn, the more bonus you're going to get in the end of the game. Now you can increase your points by starting a small business in Toma City. And you can select some people to help you. But just as in real life, not all of them are going to help. So you have to choose. Now, if the person you chose help you grow your business, you earn 1 point. If not, you earn 0 points. And you're going to see your points after each decision. Now you can play this game for 40 rounds, and we can look at your behavior. Now, let me show you one example play. If you're ready to help, if you're ready to play this game, let's just get started. All right, now, who do you want to work with? It seems like this person want to work with Chufa. Tell me why. Awesome, you earn a point. How about second time? You choose a group, and then you know how we did last time. So you got the idea. And you're going to play this game for 40 rounds, and we can look at your behavior. That's the game, pretty simple and straightforward. All right, just to remind you, here are our underlying manipulation treatment effects, but they all correspond to our model configuration. But for the interest of time, I'm only going to highlight the sampling strategy. So we have 2 conditions. You either will be assigned to this you choose condition. That is what we saw from the demo. You're going to select whoever you want to work, or you will be assigned to a you meet condition. And there, you are going to meet the people we prepared for you, and we make sure that you make random people. So that is going to mimic our random sampling condition in the simulation. All right, again, those are the 2 outcome variables we want to look at. First, partner choices, like how many times you interacted with each of the group. Now, second, we want to know reward estimation. So in the end of the game, we ask, now for each group, how many times out of 100 do you think working with a person from the group is going to give you earning 1 point? So ideally, they should say 90 points for all of the group. But again, let's see our participants' performance. All right, now, this is the exciting part of the empirical results. Let's first look at this partner choices here. First, from this random meet condition, we're seeing our participants are meeting the 4 groups like Tufa, Aima, Roku, and Weki 10 times each, which makes sense. It's random, like we made them to do this. All right. As a result, their estimation about the reward is pretty good. Now, if you look at this on the x-axis, this is estimated reward from 0 to 100. And these are the data from random meet condition. And again, this dotted red line here, this is raw truth. This is 90 points. And we're seeing the participants are getting relatively good estimation, especially for the top 2, although the other 2 is kind of off here. Now, what's really critical is to compare this condition to this you choose condition. Now, when our participants choose their own partners, what we found is this. Our human participants also selectively and predominantly interacted with one group, but they underexplored the other 3 groups. Now, as a result, they're giving a good estimation for the group it interacted most, like the red one, but the estimation for the other 3 groups are way worse. Another way to say it, like probably you're already starting to see this parallel pattern between simulation and human data. But I just want to emphasize, when our participants have no prior bias and everything is kind of new to them, they didn't really want to play bad, or they didn't have any malicious intention in the game. Now, in the end of the game, participants, whoever they make their own decisions, they follow this Thompson sampling, they now think the 4 groups, Tufa, Aima, Rekun, and Weki, are much more different from each other as compared to participants who randomly meet those 4 groups. And we think this kind of adaptive expression, like use your past experience to inform new decisions kind of process, is contributing to this difference. All right, now that's it about this empirical results. And I'm just going to quickly sum up here. I know we're doing very good on time, so maybe we could save some more time for discussion. Now, just to conclude this current project here. Now here, what we wanted to do is try to find the reason on why people develop inaccurate stereotypes in the first place. Now, our explanation doesn't require any of these previous assumptions, which, by the way, in psychology, they are the current state-of-the-art explanations. But by using computational modeling, here we are trying to offer a fourth explanation, which is this adaptive expression. Now, throughout our simulation and human data, we found that actually, adaptive expression, although it helps it helps the participants to increase their benefits because they're earning maximal rewards here. But at the same time, it is creating a societal level problem, which is biased impression. And some more implication, like a little bit larger societal level implication. Now, what I found is really interesting is that this work actually is showing that, like diversity might be effective in terms of reducing bias. There might be a leap here, but let me just walk through what I mean here. If you think back, like our participants experience, whenever they were assigned to this random and meet condition, that is where they meet like 10 people from each group. It's like a diverse social environment where, you have equal representations from different groups. And that is the condition that we see people less likely to form bias impressions. Where compared to, we don't have any diversity intervention, we just let people explore based on their past experience. That is more like, a gradually segregated, stratified kind of society. And that kind of society is not ideal, apparently. And then we think, having some more public policy that try to increase social diversity can help to mitigate intergroup misunderstanding. A second implication is on machine learning and fairness, social bias social bias and machine learning kind of topic. Maybe this group might be interested in that too. Like we know right now, the current machine learning systems, sometimes they're producing social harm. For example, they're producing really outrageous kind of images relating to certain groups with certain kind of images, or producing really racist kind of text out of the kind of black box model. Now, there are a lot of efforts to try to understand, why do machines bias, and can we have some more effective interventions to reduce machine biases in general? And maybe like what our work suggests is that it's not very effective to blame the engineer or to blame the input data or the whole algorithm design. Of course, they're the problem, but then maybe even though we could address the problem, having good intention, having diverse input data, training data, and having a like kind of fair algorithm design, we're not going to solve this problem. That is because this machine learning system is going to evolve continuously with our human behavior. And then if what we're showing here makes sense, that means that, as long as we have this continuous interaction between human and data, we are going to see this bias impression emerge. And so what that suggests to me is that maybe we should start to think about kind of different ways to think about this problem, really to think about machine bias in a more dynamic perspective and a more longer term continuous kind of perspective. And how can we do this intervention given that this impression formation is forming adaptively over time? And finally, maybe we could open up some discussions here. I think our work also have implications for filter bubble, like polarization online kind of effect. If you think about, the recommender systems are fundamentally using kind of similar architecture, then maybe there's some conversations should be happening here. All right, with all that, I wanna, just stop there and thank you all for your attention, and I'm happy to take any questions.